Series that have the form of the sum as n goes from 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times the quantity of x minus a to the n are infinite series. We know that because the sum goes to infinity. Finite series of this form are represented t sub n of x equals the sum, now as I goes from 0 to n, we're now using n in a different way, so we need to change the index, of the ith derivative evaluated at a divided by I factorial times x minus a to the I. It's all the same stuff, except now the index is I, and we're capping it. Instead of going to infinity, we're capping it at n. These are called Taylor polynomials centered at a. Because these represent a finite number of terms, they are a partial sum for the actual infinite series. The infinite sum is the limit of the sequence of partial sums. For any partial sum, there's a remainder. And for any n, the remainder of the Taylor series is r sub n of x is equal to f of x, the full-on function, minus t sub n of x, that's the partial sum that we would have added together. And now this implies that f of x is equal to that partial sum plus the remainder sub n. That should make perfect sense. Now, if you've been watching this series of videos, I keep saying things like, if there's a Taylor series expansion, if, now we're getting to what that if is about. We have actually a theorem, and it says that if the limit as n approaches infinity of r sub n of x is equal to 0, then I'm actually going to kind of roll up a kind of proof in with the statement of the theorem. Then it will follow that the limit as n approaches infinity of t sub n of x is equal to the limit as n approaches infinity based on this equation rearranged. The limit as n approaches infinity of f of x minus r sub n of x, which equals, now look, as n approaches infinity, f of x is unaffected, so this is f of x. And our supposition is that the limit of the remainder is 0, so that part of it goes to 0. So here's the point. If the remainder is 0, then the limit as n approaches infinity of the nth degree polynomials is equal to f of x. We can conclude this by saying that if that's true, then f is equal to the sum of its Taylor series. So all that if is really based on if we can show that the remainder is equal to 0. For that, we have something called Taylor's inequality. Yeah, he's all over the place on this. Taylor's inequality is useful in showing that the limit as n approaches infinity of r sub n of x is equal to 0. It states that if the absolute value of the n plus first derivative of x is no bigger than some number m for an interval x minus a less than or equal to d, then the remainder r sub n of x of the Taylor series satisfies that the absolute value of the remainder sub n of x, so the remainder after the nth degree polynomial, is less than or equal to that number m divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1 for the interval x minus a less than or equal to d. Now, this n plus first derivative in absolute value being less than m, that should bring to mind something that we saw when we were looking at approximate integration. I'm thinking the midpoint rule, the trapezoid rule, where the second derivative was less than or equal to some number k on the interval, or for Simpson's rule when the fourth derivative was less than or equal to k. Yeah, so something similar to that is happening here. Let's see what this looks like in action. For f of x equals e to the x, the nth plus first derivative of x is equal to e to the x for all n. So as long as d is positive, and then for any number d, the absolute value of x is less than or equal to d, so x is within an interval from negative d to d, then the nth plus first derivative of x is less than or equal to e to the d, right? Just replacing x by d. And by Taylor's inequality, r sub n, the remainder of the n terms that's been added, is less than or equal to e to the d divided by n plus 1 factorial times the absolute value of x to the n plus 1. I put a period there, but now it looks like a weird exclamation mark, so I'm erasing the period. But the limit as n approaches infinity of e to the d divided by n plus 1 factorial times the absolute value of x to the n plus 1, as n goes to infinity, e to the d is unaffected, so I can pull out e to the d, and that's going to be times the limit as n approaches infinity of x absolute value to the n plus 1 divided by n plus 1 factorial, and the ratio test would show us that this is equal to 0. Now, what we've got is that the remainder in absolute value is less than something that's going to 0 as n approaches infinity. Thus, the limit as n approaches infinity of the absolute value of r sub n of x is less than or equal to 0. Well, it certainly isn't less than 0. It's an absolute value after all. This means that the Maclaurin series for e to the x that we developed is valid, and we can declare that e to the x is equal to the sum as n goes from 0 to infinity of x to the n divided by n factorial for all x. We can dispense with the if. Now, just a note here, showing that the limit as n approaches infinity of r sub n of x is equal to 0 is part of showing that there's no more if. It's part of showing that a Taylor series actually represents a function.